I'm Remus Hanea, a research scientist in the RL, and one investigator on a solar project. One of those projects is with Equinor, who's a longtime founding member of ERL. And I have a great pleasure today to introduce two colleagues from Equinor. The first is Remus Hanea, who I've known for a long time. Remus is the leading advisor in reservoir technology, assisted history matching, and optimization decision-making in the Subsurface Discipline Excellence Department in Equinor. That's a very long position. It takes longer to say it than to be there. He has a background in applied mathematics, 15 years of experience in uncertainty quantification, data assimilation, and optimization decision-making, which are all topics I've been very interested in for a long time, including when I was at Schlumberger many years ago. So I've known him for a long time, and I'm glad to have him here. Remus is also a part-time professor at the University of Stavanger. And then with him is Tobias Klemm. He has a background in business mathematics, and he's been in Equinor for about 5 years. He works in the role of project leader with the decision optimization project within Equinor. And they're both research scientists, and I've had a preview of what they're going to present, so I'm very interested in how to make connections between scientific research and people making decisions. So please welcome them.
Thanks for having us here. As I said, I started working in data assimilation about 25 years ago in atmospheric chemistry. Then I moved to hydrology and oceanography. Then I moved to groundwater. And then in the last 13 years, I'm doing subsurface engineering, which means my career goes down my age. But I was new to this topic. I am not a geologist. I didn't know anything about enough to know. But then I'm here in front of you after a few years to talk about a shift in working in subsurface, and then that shift goes from a model-driven optimization to better decision making. And I don't know how much you know about reservoirs and decisions there, but if I ask what do you think about optimization, if I say optimization, what do you think about?
Yeah.
All right, something else. Think about I'm thinking about optimizing or minimizing or maximizing a cost function. And then we do this in different domains, but you do have a cost function, you do have something to optimize, and then this usually is done under some constraints and by playing around with some controls. So that's basically what I have in mind optimization. I have some controls that I'd like to tweak in order to optimize a certain function or certain objective. And in reservoir management or field management, what do you think that objective could be?
MPV.
MPV. What's MPV? MPV it says net present value. It's a formula that is basically calculated on the cash flow. And the cash flow is CF. Basically, it's a simple calculation where it involves the water production and the rate that you produce oil and gas, which is a positive side. But then if you produce oil, you just produce water in the same time, because sometimes you go and inject water to keep the pressure and move. Yeah.
Not risk.
At the end of my, so that's basically what's happening is I'm the old person, he's the young one, so I'll show you how things were done now and see the future afterwards. But yes, the risk was part of it. And I'll come back to risk. So, but basically that's what we're doing, MPV, and there was not much risk in it. If you look at it, they're doing this for the last 40, 50 years. And they do manually. The risk was not part of it. They were using one model. That's another thing that I should say. I make a disclaimer. I'm basically in the world of multiple realization and uncertainty quantification. And then, so we have this cash flow, which depends on oil and what oil, and water treatment, and some of the other things here, which basically tells you that I have a positive cash flow if I produce oil. I have some negative values when I'm injecting water or I'm trying to handle water, and I have a rate of discount, which basically not risk really, but it tells me how I'm going to put the weight on the price of the oil in short term. And the water production, water injection, and oil production are basically output of an formal output of a reservoir simulator. And the reservoir simulator, or the formal, explains the physics in the reservoir and will tell you, given some certain condition, how much I can produce, how much I can inject, and gives this forecast. And this basically depends on how I'm going to develop my field, how I'm going to inject, or if I inject water or inject gas. It also depends importantly on geology, on the input of how the subsurface goes up, how much flow can go through a rock, if it goes or not, it doesn't go, the quality of the oil, and so on and so forth. But this puts in the problem a forward model, a model that will give me a forecast. And it depends on two variables, an X and a U, and the states of the reservoir and the control input. But then, in general, if you want to make an optimization or make decisions, you have to take one thing into account, which are the uncertainties. You can't make a good decision if you don't take uncertainties into account, and those are present in our approaches. So then we have uncertainties in our states and in our control variables or decision variables. And those are, if you think about controls, will be in this kind of
well rates.
Yes. So then when you do this, you have, it's a complex field where you have subsea templates, you have FPS, so you have a lot of things there. And you want to make decisions. And I think in my view, the decisions are split in two ways. It's the brown fields, which are fields in production, which you have enough data, I have years of data and so on, and that kind of decision you can say what kind of facilities, where to drill, exploration well, and also the brownfields. Greenfields and brownfields, different decisions, and these decisions are uncertain. Yeah. So what's happening is you go to as a researcher, I go to an asset and ask, how do you want to develop your field? They say, I'm going to tweak my production rates in this way, and they give you certain numbers. That much I'm going to inject, and that much I'm going to do. And then I ask them, are you certain of that? Can we put some uncertainty on it? So that's how each of those decisions, control variables has a certain distribution, and I can make an ensemble out of it. The other one is the modes, the input. And in my case, the uncertainty in the reservoir management and field are the geology. I'm going to say, okay, I'm not usually, because I'm not a geologist or geophysicist or an engineer, I can start making fun. Because I see here the head of the department is
risky business.
Risky business. But they tend to give one value. At least the ones that I talk with is they really want to give you the ground truth. The same the geologists, the same the geophysicists, they want to give you this map of Earth, which is the ground truth. And I'm not interested in the ground truth. I think I can't do anything with the ground truth because I don't know it. And also, it's only one reservoir out there, so there's no uncertainty that the reservoir is there. But our knowledge of the reservoir is really poor. So the uncertainty is in my knowledge and in my way to transfer that into uncertainties. So what we do, instead of having one representation of the geology, I will have an ensemble of geological realizations based on expert knowledge, based on discussions, based on outcrops, based on analogs, where you start thinking how much this can vary, where to vary. So these are depending on the structure, faults, rock properties, strategic properties, and so on and so forth. So then at the end of the day, you end up with a set of models and a set of geological uncertainties and a set of decisions. And from those two, I will try to come up with an optimization. And then usually when we do optimization, I would like to calculate the gradient. But calculating gradients needs a numerical lots of numerics and analytics, and you need usually to calculate an adjoint of that formal and in terms of commercial softwares. you don't have the access to those models. So then we are working on uncertainty world. So I thought, well, not a good idea, let's avoid using these two types of uncertainties to approximate the gradient into a stochastic way. So what we do, we basically, in the beginning, we had the discovery. We say, hey, this is how the river looks, and based on that, they will decide where to put the wells, what are the well targets, and so on. What we tried to change in the last couple of years, 10 to 15 years, is that instead of looking at one geology, you look at few of them, and that few of them, as many as you can, is better. But and based on that, instead of making a decision on one single model, I'm going to make a decision on an average of those models. So that's the whole idea of what I think about robust optimization. So robust optimization is where I'm moving away from a best case or reference case, which is one geology. I'm moving to an ensemble work and say how this decision will impact possible realizations of my geology. And then the important part is I'm taking average. So then I have an assumption that each one of these are independently. So each one of them are equally probable to be a geological realization of reality. And then the risk comes in if you have an ensemble of those models, you can start accounting for the risk of the lowest ones or the highest one. You can do some multi-objective or saying I would like to get the risk here and go it upstairs. But I would like to, I have in place a way to generate this decisions based on uncertainty quantification. So what we do is usually in optimization, you calculate the stochastic gradient from it, and then if you do an exhaustive search, you should take each of these controls and apply to each of these realizations. And that will be like I have 100 realizations of my geology and about 100 controls. That will be about 1,000 simulations, which takes time in reality. So therefore, someone in Tulsa University in Oklahoma, they came up with the idea where they really use the Monte Carlo type of approach, and they decide, and then they prove theoretically that if you pair them one control with one geology realization, you can get a good approximation of the gradient. So now I have, if I have 100 simulations, I have 100 ensembles, I will do 100 simulations, and basically I will calculate the sensitivities as I do into a stochastic Monte Carlo way. So that's how we do, at least until a few years ago, how we do decisions. This is something that it's implemented in Equinor, is the best practices in how you do a decision on how to develop the field, if in case you have an ensemble model. This can be applied for one model too, but I think it defines the purpose. This is meant supposed to be to take uncertainty into account and go for a robust solution. So if you have a field in development, you start with the prior initial idea of how geology looks like. You expand it in uncertainty, you get an ensemble of models. You start talking about what decision I want to take, and there, as you said, there are tons of decisions to do. You make the decision, you get one strategy out of this optimization, which in average is best for all the realizations. And then I get the strategy, they put it in the field, they start developing field, they start doing wells, and then you get data out of it. So what you do with data, we'll try to go and improve the other part of my uncertain work, which is the geology, because at the beginning, I didn't know too much about it. Maybe I had one exploration well, I had few surveys, geological surveys. I had a feeling of how geology looks like, but when data comes in, then you can update your prior knowledge, update your belief in it, and then you will do this with the data assimilation technique, or inverse modeling, or in reservoir engineering called history matching, where you start with X, which are the geology. I had an initial idea of it, and I'm basically using an ensemble filter, or basically an ensemble smoother, a Bayesian update of my prior knowledge, given the observations and the uncertainties. So I start with an ensemble of my models. I calculate the predictions with the model for each of those realizations, and then I compare it what I observe in reality, and I'm trying to minimize that difference. I would like to switch and tweak my model parameters in order for the innovation, the distance between what I predict with my model and what the real observation is getting as small as possible. So it's a minimum variance. I'm doing this with an algorithm that takes care of the uncertainty in the measurements, uncertainty in the models, and it's something that was implemented and it's working in the industry for the last 10 to 15 years. Was invented by a reservoir engineer, which is fun. doing a PhD together with Reynolds in Tulsa. And this is the method that we use for updating our geology. So we had two pieces. One was the controls and the decision we make. And when you develop the field, you do that based on your prior knowledge. You take the decision, you put it in the field, gather data, update your models, and then you can validate your decision. Because when you do optimization, for example, I'm optimizing the drilling order for the next 20 years. So I have a field, let's say I would like to develop it for 20 years. And then after the crunching the numbers and giving the uncertainty, the strategy will be drill the first 2 wells in the first 2 years, then the next wells in the next 3 years, and then, but if after you drill the first 2 wells, whatever you believed at the beginning changes because you have new information. So you better go update your models and validate, hey, the next decisions I made are still valid or not. So that's what in the world of reservoir management is called a closed loop reservoir management. And this is basically done by, if you recognize the arrows and stuff, someone from control and system theory, because that's how they know how to express physics and dynamics. So you start with optimization, the decision, you put it into the system, you collect data, you update your models, and then you do your decisions. And this is an evergreen process, and this is basically what we try to follow up as best practices in Equinor. So we have fields in production, and every half year there is a new model revision where they collect data, they update models, they validate them, then they look at the further decisions and go so on and so on. But then the important thing is that I said we wait for the data to come. So then if you look at it, it's like a post-mortem, this post-mortem analysis. So I have to wait for the data 2 years to know if my decisions for the next ones are good or not. It's a model-based thing where uncertainty is taken from the geological part and brought up into this mechanism of both history matching and optimization. It gives you a single best solution. So there are no possible alternatives. I don't think about possible alternatives. I'm taking the decision at this moment in time without thinking what's the effect of a sequential decision. If I do these 2 wells, how the others are changing. I can't do this today with this approach. So I have to wait for data, get them, and change my opinion afterwards. So it's a myopic way of looking at decisions. And the data that comes in is primarily used to update my models. I don't do too much out with the data. The data is there to give me something to condition my models on and improve my prior knowledge of geology. And then I've done this for lots of years. And then about 6 years ago, I started working in the University of Stavanger with Professor Reza Bravo, which is a well-known figure in the decision analysis and decision quality. And then we had our first meeting in Stavanger, and then he said, "Can you tell me what you do?" And he says, "Why are you doing it?" Why are you doing this? Yeah, you say that you reduce uncertainty in the geological understanding, you understand the reservoir, you show me this nice strategy, but why are you doing that? And I didn't answer the question. He says, "Yeah, but did it change your decision?" I don't know. I never thought about change this. If I use uncertainty, it will change or not my decision. So you better think about it. And then when I start thinking about it, how can I use this uncertainty quantification and how this impacts future decisions? So move away from a myopic version to something that takes into account more than not just the uncertainty in my models or uncertainty in my data, but look at what if scenario. When someone would come to me and says, "I'd like to optimize the drilling order," I could have asked, "Yeah, but why you want to do that? Is there any other alternative to maybe think about some other ways to do it?" I haven't thought about it. But with the time passing, I start thinking about it. And that's when I say that I'm going from old school to the new school, where I've done this for a long time. And then I think I've changed my mind in the meantime, and I would like to basically try to gradually move from the way I'm doing optimization and link it or project it to a decision analysis structure. So I can use the philosophy and the theory in the back of decision analysis and structuring decisions in the optimization world, in the data science world, to make possible better decisions in the future. So that was my part of the talk. Any questions on it? Yes. So I think I see the dilemma you're being faced, because you're making a decision and then you act on it, and then you basically all you do is you move along this one path. Have you looked at like historic? Maybe if you get like the whole field situation where you get historic data, but the decisions were not optimized, and then you go back and see how would that fit in that model? I will give you the realistic answer to that. We asked it, we've been denied. Okay. That would be really helpful, because that could, you know.
Now we're going to do that in the future, based on what you're going to see next time. Yeah, will be the best way to do is to just go back and learn from the mistake. But I think we've asked those questions. They said, nah, it is not of interest. We should look how we improve this.
Learning from mistakes, can't have that.
Yes, you can.
Yeah, maybe similar question. How many models did you do, and what's the overlap with between the models in the real world? Like, is there like a model that you completely
What's the real world?
like the well or the formation?
We don't. I don't think I will ever know the real world.
No, I mean between the model and the outcome of the.
So between the model and the outcome of
Production.
The production.
Data
Yeah.
2 years later.
yeah. So that's what we do usually. So what we do with this methodology. So because I don't know the geology, I can envision possible realization of that. Yeah. I have a geology concept or few geology concepts, and I'm basically simulating or putting some distribution on top of these parameters, and I can basically sample different rock properties, which gives me a set of realizations. And those ones, I'm predicting what will be the production rates and observations, and then I look at this difference between them. After I do the update, I always have a set of data independent of the ones I use in my history matching to validate if those predictions are good, because I'm personally not interested if I'm going to match every well historically, because I think the most important part of the decision are done in future. So I'm interested in, if I change this geology in the way that I change it, are these going to be able to predict my dynamical behavior in the future? So what I do, I just either take one well away, like in AI, take it one well away, and I'm not using the data, and then I validate to see how close I am for this data, or I'm splitting the data in 10 years of doing history matching and updating, and then another 1 or 2 years afterwards where I'm validating my models. And then if they fail that one, then I have to go back and redo the geology or look at uncertainty quantification and redo the whole work.
One quick question. So it's very intriguing not to see the left side, what you traditionally do, and then on the right side, some, the sunrise. So can you tell us a little bit more about how you formalize that? So what I'm thinking now is that the space of decisions is often very low dimensional. Not always, but often. Do I develop this field or do I not? Do I drill this well or do I not? So
you'd be surprised how big it is. I think
so. I was thinking of that transition as being some sort of collapsing the uncertainty that you've been able to characterize to make a decision that is sometimes binary or lives in a lower dimensional state. So how do you formalize?
Yeah, so that's what I mean. I had a slide. So before that, I had a slide. But so when we start the project, usually when we start a project about developing something, the first thing that they do, we're going to go through modeling. So then we go open the seismic, open the stuff. We start putting the top, the bottom, the faults, start making pretty much very, very nice ways of filling facies and so on. So we build up this whole process of a full field model and so on. And then you get the data, you reduce uncertainty. And then usually when you end up with 100 models and give it to someone to do decisions, they will likely say, yeah, but I don't know what to do with 100 models. And maybe I can pick up 3 of them. Maybe P50, P90, P10, and they just picked up 3, and they end up with one decision, like you said, drilling order. But so it's, if you look at the pyramid, the uncertainty grows, it's getting smaller and smaller, and you get one decision. But if you turn up the pyramid, I think starting with the decisions from the start and then picking up what models I'm going to use for it. If I want to drill a well in a sector and into a part of the model, which is a sector there, do I need to use my full field model, or I can get away with the sector simple model? What do I need seismic? Well, maybe not. Do I need this? So I think this is how we're thinking. And the more important part is, you're right. Beforehand, we had an asset and we had 1 or 2 decisions. Nowadays, with the fact that we're not looking for big mammoths, an exploration. We're not looking for the next Johannes Reservoir zone. The problem starts getting around what's called near field exploration. So we're looking around the fields that are there, and then the problem starts from one asset to an area development. So I have this development, and now I'm going to ask myself where I'm going, how I develop. Do I tie this for the main, on the main field? Do I drill the well from the FPSO, or I'm going to put such a template? If I go this, do I go through the other exploration, and if I find a discovery? So then the space of decisions becomes so big that this, what I've done before, fails to deliver in the way that I would like to deliver.
Okay, that's very useful. That answers my question.
Exactly. So I think there was a change in how we looked at the problem. Sorry. And
So as you guys were talking, I just wanted, since we also talked yesterday, there's a lot of work that's been done from our friends across the campus in EECS on partially observable Markov decision processes, for example, and other related topics that look at some very precise questions related to sequential decision making that could be a great resource to also draw from. And the second point was, there's too much information, data being generated in one end. Every simulation you do produces an enormous amount of data. But to make decisions, as I guess Ruben just pointed out, requires you to have the right kind of features or the right kind of subspaces over which the decisions could be made. And there again, I would say that there's a fair amount of work that has been done in looking at sequential design of experiments or optimal design of experiments, where experiments here are to extract the features that allow you to make good decisions, even not the exact decision, but it allows you the ability to make good decisions. And I think that is something also that could be useful.
another question.
Yeah, here. Sorry, I'm just curious about, have you ever met with some cases, like, because you're calculating the mean of the gradient, right? So have you ever met some cases like the gradients of the ensemble members will counteract with each other, and it will influence optimization or the decision making later?
When I calculate the gradient, I calculate the gradient over an average. So I take the average of the whole cost function. I calculate the gradient over all of them. But then what I encounter is that the approximation of that gradient is not good enough in cases where the controls are more complicated and non-linearities are present. So this link with one geological model and one control variable might be nice in theory in small problems, but then sometimes I have to put more calculations on it to make the stochastic gradient converge.
So we can maybe continue with the talk.
Yeah. Sorry. I think you already introduced my next slide, actually, where we are looking into like one of those field applications we had a few years back. So we had this problem of like, we had a platform here, it was connected to some infrastructure they were producing already, and now they were like thinking about like, how do we produce this thing here? Should we place like a new infrastructure with new subsea templates there and drill from there? Or should we drill like 9,000 meter long wells? So it's like kind of down and then like along. And it's like, and then you have like two discoveries, so it's not just one, it's the second one as well, and like where do we place the well? So it gets like very quickly into many, many more decisions you have to make for this one project. While Remus would provide us like with like one optimal control for one thing. Here we are like thinking about how many wells, in which order we want to drill it, where to place it, and so on. And then also like thinking about the bigger picture. And so we have in the subsea development, for example, decisions on like the template sizes, right? How many templates do you want to place? How big should they be? Should you drill those extended reach wells, which are 9,000 meters long, or should you actually, and how many do you want to drill of those? Which discovery do you want to include? Like, so do you just take one of them? Do you take the other one of them? Do you produce both of them? And then they currently drilled two of those 9,000 meter long wells into each of those discoveries.
And then it's like the question about like, should we wait for the data there to actually make the final decision and like do all the work? Or can we be a bit more proactive and actually kind of think about an optimal strategy before we get the results, but then update or then know already, like depending on the information we get, what would be the next best decision. And then it comes to a point where you think, okay, how do you actually decide in this situation? And then it is us who is working on this subsurface idea, but then you have someone who does not like to drill 9,000 meter long wells. It's like a huge job to do that. The drilling engineers, they don't like that. It costs too much money. It takes too long time. Too many things can go wrong. There's a lot of risk involved there. So they would prefer this way. Then you have partners, like we partner with Shell and Total and Chevron and so on. So they might have something to say, like how do we best connect this platform to other areas as well. So this is just one screenshot, but we have this like several times where then each partner tries to kind of like think about, okay, where should we actually like spend our money on and invest in it? And coming to the question, like how to decide in this situation, I want to go actually like one step back and ask you, why are we actually making decisions? So you can take, if you have a smartphone, you can scan the QR code. In a few minutes. If you don't have your smartphone, you can also like talk to me at that time. Like, why are you making decisions? Why are we as a company making decisions? But it also like everything what I'm talking about is also applicable for your private life as well. So it is not just like in our big company that we want to make lots of money. Poker. We want to poker, right? We want to gamble a little bit. Yeah. I will come to that in the next one as well. Be happy, yes. Yeah, life quality. Yeah, optimize recovery, perfect. To affect future outcomes. Yeah, we have to. Yeah, that's a good one, yes. We have to, like someone tells you, you have to decide between red and blue. Life is full of choices, perfect, yes. Risk. Yeah, you want to mitigate risk, right? You have maybe like, okay, I usually bring up something about like a risk of getting wet in Bergen, because in Norway, in Bergen, it rains a lot. And then there's a risk if you don't bring your rain jacket and your umbrella that you're gonna get soaked on like a 2-minute walk. But we are like here with super weather, so I can't bring that one. Yeah, but it's kind of like, a lot of ways how we can, like, why we should make decisions. Then there came a new one. Learn something by doing, yes, perfect, yeah. No, very, very good, yeah. I will give you another question as well, related to the approach Remus presented a little bit. If you see any problems with that, we can go through that one fairly quickly, because I actually want to go to the next slides as well. It doesn't adapt, yeah. It's like one time and then we give this to our decision makers and then we don't see about this in the next 12 years. Yes, great. And the last question now for this section, what makes decision making complicated? In your views, if you think about what you do every day at work, what you have to decide, or like if you think about, okay, in the future, like if you have to work for a company like Equinor, what is perfect uncertainty, stakeholder biases. So we have those stakeholders as well, and like making one decision involves many, many more people than just like the two of us. Consequences, yeah, different objectives, very nice, very nice. Can't please everyone, very good, right? So the driller who doesn't want to drill 9,000 meter long wells, right? That is one objective. They have their KPIs of like reducing drilling time and so on. But the subsurface people, like in Remus' position, he will optimize an optimal well path, which is 9,000 meter long, and which gives you like the highest recovery. different objectives. Surprises, consequences, incomplete information, very good. I'm not sure actually the future is unknown. Yeah, uncertainty.
I like this.
And so the interaction is gonna continue now a little bit. I think you can still respond to this as well. But I'm gonna poker with you now. Not really, but I got a coin. I actually got this coin in Norway. So in Norway is nearly like cash, like cashless. Everything goes like through Visa and MasterCard and so on. So, but I exchanged a bit of money to US dollar, and then they don't give you the full amount. So they gave me like this thing, which I don't really know what to do with. And it has a little hole, right? So that if you lose your wallet, you can always attach it to a string and like hang it from your. So, but we are going to play like a little throw coin thing. So the task is you guess what is the top. It's a doesn't have really a head. It just says Kingdom of Norway, and the other side is a 5. And Remus is going to throw this in a few minutes, and you can decide now: do you want to play or not? Emil says yes, he wants to play. The thing is, he doesn't know all the information about the game yet. Right? Playing costs $1. Right? It sounds like, so we didn't talk about this actually before. And now like we were thinking about like KPIs and objectives and so on. Like so what do you want to achieve with winning?
Fame.
Fame. Yes. Good. Okay. Yeah. I have. You can win a pen. So that I bring this example, like there are people who collect pens, right? And then they're like, wow, this is like a super silver pen from Norway somewhere, like that needs to be like framed into my collection. You can win the coin if you want to. If you're a coin collector, you will value this coin more than $1 probably. Actually, I think it's like $50 worth in current terms. Or I bought a bar of chocolate, Norwegian chocolate, supposed to be very good. And in the end, we can kind of just think about this. And you're going to throw this coin now, and you will be the only one who's going to know what the result is going to be. Is there someone else who wants to play? No.
For $1, you can get a chocolate.
Yeah, I'm also I'm game, but then we have to split now the chocolate bar.
Second one. So now we can think about if we would. So I was considering to kind of increase the numbers a little bit, right? Instead of like $1, I would ask for $1 million to kind of bring it a little bit more into the context of what we are working with in Equinor. And then a pen has some value, right? The coin has some value, and the chocolate bar has some value as well. And now we could ask Remus, do you want to give us some information? Right, so I can now ask Remus if he wants to give some information. If he wants to pay for something, then he has to think about, okay, what is kind of the information actually worth? Right, so like I said, the coin is just half a dollar, so it's a bit like.
I only want 1 bit.
But wait, you paid already, and the outcome has been decided.
Yes, but he doesn't know it yet.
Oh, so it's still random framing.
Yeah, okay. So it's and this is exactly what we do with the reservoir, right? The reservoir is the coin.
Yeah.
The reservoir is down in the ground, but we have no idea about it.
Yeah.
But now Remus is your seismic survey.
Yeah.
If you want to pay him, but you can also risk it and don't pay.
I'll give you $1 for the value of the toss.
Oh, actually, he is.
So right, Remus has another objective. He also wants to make money. He's another company who has kind of share in this information. He knows that if gets this bar of chocolate, that this bar of chocolate is around I know, $4.
I'll give you $1 now and $10 tomorrow.
We're leaving tomorrow, paying for Robert. I know that information, so we're not going to get the money on the plane.
Sounds like a bribe.
It's not a bribe, that's some of the questions that were asked by the people that are doing seismic surveys. You get it.
And now,
Exactly.
so now you can say something if you want to accept.
No, I'm not going to accept it.
You're not going to accept it? Because then the next thing would be, is the information Remus gives Hanea actually the right one? So then I could have asked Hanea again, like, do you want to continue with your bet, or do you want to get out of it?
Yeah.
Kind of as an insurance type of thing, right? Hey, like, I don't trust Remus, so I'm not gonna get anything.
You still get a more chocolate.
I want the coin.
You think it's the coin as well? So, but this is kind of just to kind of like take these kind of like abstract decisions we make in the business to like something like fairly simple and we all laugh about, right? It has like no impact, right? It's $1. Yeah, okay, right? The bar of chocolate is not the big thing, right? So, but then if we're like thinking about this, if we multiply this by 1 million, 2 million, and so on, so it gets kind of quite high stakes, and people like start gambling a little bit without the exact information they have, without the exact kind of objectives they think about everyone else has. So now we could have also thought like we build some teams, right? And then like one team wants the coin, one team wants the chocolate bar, and then you have to think about who is going to play this game because there's only one player, and then they would have to compete and so on.
It's also a matter of when do you stop?
Exactly.
Like gathering information and then you actually have to make the decision. And I think I thought about that quite a bit too in terms of like when is it enough and then you move on. And I always think like, and then I think of Pareto, right?
Yeah.
Is that you gain 80% of the outcome with 20% of the effort, right? And the rest of the information you gather, you only gain so much, right? So you have to sort of find a way
Exactly.
to
And we are going to come to that as well.
No
if
one
I
to
actually have
hold
time.
them, no one to hold them.
So then we talked about like why are we making decisions, and now I'm just like thinking, okay, what is actually a decision, right? Like I may have to say head or tail, basically, which you never did.
Back his dollar too.
Yeah, exactly. So, damn it.
Then he got the chocolate bar. He is smart. He was the only one who played.
And we see like that a decision in the kind of like formal definition is kind of an irrevocable allocation of resources. And these resources can be anything, like can be money, can be your time, can be my time, can be people, right? In businesses, you have to decide who works on this. Also, like then thinking about how much is it worth it. It's assets, it can be opportunities, right? That you say everyone else also made the decisions because you all said, no, I'm not going to gamble. Right? It's kind of like you all made a decision here to not gamble, and you basically allocated a resource we would call an opportunity to actually win a chocolate bar.
And mine was revocable.
Exactly. Yeah. And then actually that's kind of what I asked you the next in this Menti thing is what are actually good decisions, right? So what I've heard before is something like a good decision is one that has the highest chance of getting the best outcome. That means that this example, if you have an uncertainty, you have a chance here. With 1%, you win $100, and with 99%, you lose $1 million. Seems to be. I wouldn't play that game, but we could have done that. But given this definition of some people saying it, this will be better than this one where you would say with 99% chance you will get $99 because $99 is not the highest outcome you can get. And so there are like some biases about decision making in not just in Equinor, but also like in general, like in in our human brains, because we're kind of like somehow not wired to make those rational decisions sometimes. So my next question to you is, how do you define a good decision? In your view, like, how would you say, I made a good decision here? We talked about that briefly in upstairs now. How would you kind of think about tossing a coin decision, or thinking about buying a car, choosing a flat where you want to live, where you want to work? And in Equinor, it would be something like, where do we want to invest our money in? Is it drilling 9,000 meter long wells, or is it gonna be placing subsea templates down there? It's defendable, yes. Like, you can actually like explain it to someone else, and then everyone else should kind of follow that logic as well. More gain than loss. Predictable. Transparent. Very good, yeah. So that's like kind of on our journey is kind of the transparency quite a big issue, because then you have one department making a decision and the other department is making another decision and they're not transparent. Maximize expected value. Yeah, integration of all information. Yeah. Positive expectations. Very good, yeah. No, this interesting. Like, keep them coming. Like, think about this a bit more. And I will give you my decision here. It's a rational decision. It should follow the objectives. Yeah, so that if you are a coin collector or a pen collector, then your objective is to acquire more special coins or more special pens. Then this is your objective, and that's consistent with betting and playing this game. And it should be consistent also with the information and the preferences and also the alternatives we have available. So here you had an alternative of gambling and not gambling, right? So then we could have and then I may have the possibility of buying more information and not, and deciding about the price. So many, many more decisions to come. And so going to this again, yeah, was it a good decision or a bad decision, do you think? To play the game even though you didn't pay? For you, it was definitely good. Good, yeah. Right? It was even a good outcome as well. Yeah. You could have lost $1. And here we have to distinguish a little bit between outcomes and decisions. This is what we can influence, our decisions, how we make decisions. This one, we can't. We want to have high quality decisions, we want to have good decisions. And then in an example here, you're at a party and then you think about driving home. And you think about, okay, do I drink that evening or not? And you say, I know I need to drive home, so I'm gonna not drink that evening, and I will drive home safely, and I'm gonna be fine. What could happen as well is you stay sober, but another guy crashes into your car, right? Or like something else happens, right? The car says, okay, no, I don't know anymore, because it's like some computers now. And you still had an accident. That's like you made a good decision, but the outcome was not good. What you could have also done is that, I don't care, I drink, and then I drive, and you arrive home safely, right? So you have a few beers, and then you get into the car, drive home. You know the way already, right? Everything's fine. This is not to encourage you to drive. And then of course, like what could happen as well is you drive drunk and you have an accident. The main message is here that these outcomes are influenced by our chance, by some uncertainty which is there in the world, which we can't influence, but we can influence our decisions. And that is then in the end our value creation. So we can decide in which kind of like row do we want to be, but we can't influence in which column we are going to be. Because there are other impacts.
But there are experiences that would weigh the columns.
Yes. So there are. So usually we would say that a high quality decision has a higher likelihood of a good outcome, but it still can still happen, right? And then if you have a low decision quality, it's a bit more likely that you have bad outcomes. And then to support all of this, some people thought about this decision quality framework. And this is, has been developed in, I don't know, 60s or something like that, where you should say, okay, to define what a good decision is, you should follow those 6 elements as much as necessary, but not too much, right? So there is this kind of like 80% to 20% gain thing here that you would have to say, okay, we have an appropriate frame. So we have to kind of get together, get the information as well, which is here as well, meaningful and reliable information. So Remus might have not given you the right information. So you could have considered to say, okay, we don't need to buy this information because we actually don't trust him. We have to think about creating doable alternatives. So in this case, if I would have just kind of given you, you have to gamble, you have to play this game, right? It's kind of like you only have one alternative, right? But then there's like, okay, you also cannot choose to play this game. And then you could think about, okay, are there any other like more creative alternatives where you would say, okay, wait a minute, Tobias, like I don't want to play now, but I want to first have someone else play this game. And maybe then afterwards I decide, because I can update my beliefs on, is this coin a fair coin, for example, or is Remus giving us the right information? You have to have clear values and trade-offs. So this is especially if you have many stakeholders involved, if there are like different departments, have like be clear about them and then think about the trade-offs. Should have something like about logical correct reasoning. So that would be then like a bit more like mathematical decision trees, for example. And in the end, you also have to commit to it. So what could have happened is like I may would have said, yes, I'm playing. And he would have said, yes, it's hat or something like that. And then, but then in the end, he would have kind of like dropped out and said, yeah, okay, actually, no. Yes, sorry.
You know, you said good decisions are rational decisions. Would you say like Metropolis Hastings is a good decision algorithm?
What? I'm not familiar with that one.
Remus?
Which one was it?
The Metropolis Hastings algorithm. It's an algorithm that goes into the. So you want me to answer the question?
Yeah, I mean, what's rational about taking a chance? If from one interpretation of what rationality is, of course, you could change the definition of rationality. But so I would just want to get to what you mean by rational.
It has to be consistent with your beliefs, with your preferences, with the decision makers' preferences, alternatives. And that you can follow the logic as well. I don't know the. I will. You can discuss it after.
What about the time that the decision takes?
Yeah.
Is that considered?
Yes.
Because for me, for example, I would not play if I don't like the chocolate. It's gonna lose my time in playing for a prize that I don't like.
Or something you don't know. Yeah. So that's kind of like consistent with your objectives, right? You don't know, do you actually like this chocolate? So now I made the chocolate. I don't know if he even eats chocolate. Right. So now he's like, oh, shit, now I can share it with the whole department also. Right. So that would be like associated with your beliefs. But then of course there is kind of a timing in here as well. Right? Because I was just asking you like out of the cold, do you want to play or not? And you have like just like a few seconds to think about this. Do you want to risk $1 or not? Right. Then it comes a bit to your risk preference as well, where you would decide that, okay, I don't go for this because I don't know enough information. So then you would come into this information collection where you would say, okay, I need more information to actually make a rational decision in this case. Like if I would have had 2 or 3 different types of chocolate here, we could have had a chat about, okay, which one would you actually like to prefer? And then we could have gambled on that one. And then what we do see when we talk to our colleagues in Equinor is that they think that this process takes a lot more time and is super inefficient, but you can actually like scale it fairly quickly. Like you just have to think about, okay, like who is the decision maker? In this case, it's you. What are your preferences? Maybe you prefer dark chocolate more than milk chocolate. Then you would have said, okay, I'm out, right? You don't even have to do the whole thing. You've already come to a criteria where you have to say, okay, I can't do it. But then you could do like all the other steps as well. Okay, what alternatives do I actually have as alternatives to play or not to play? We do this for these examples very, very quickly in our head. But then in a bigger setting, we have to kind of start considering those elements, at least in some sense. And then you have to kind of say, as you pointed out, it's like, is this 80% versus 20% gain in the end? And where you really have to consider what is actually enough to come to a good conclusion. So we are actually done, but I think I have another 20 pages.
Do we have to make a decision?
5 minutes.
5 minutes.
Yeah.
I will see like if I can. So coming back to this example, right? So what we did is, so I'm going to skip this as well. So that's kind of just to illustrate a little bit that each department will optimize in their own cluster. Like Remus is going to optimize, and then there is someone in drilling and well who's going to optimize, and they all come to a different conclusion. And now we are introducing this decision quality principle, and we are introducing this Prisma tool we're working on. And what we are doing there is we start with some framing, some facilitation, and then we create some decision models from the facilitation. So it's like, how do our uncertainties relate with the decisions and the value in the end? And those can be transferred into decision trees. That's something our engineers are familiar with. Inference diagrams is just some compact stuff they have no idea about. But then they can follow the logic of decision trees easier to actually come to an evaluation, and then in the end also like to execute it. And now I just have a few like screenshots of the tool, what we do. So then you would kind of, in a framing session, come up with your objectives, for example. So in this field development, it was reduce CO2 emissions, for example, maximize net present value, maximize gas production to supply Europe. But you also have something like increased lifetime effect on the platform, right? They have some limited time depending on the production. And then you start writing down issues, which can be decisions and uncertainties, like you don't know the production in the future, but you might get some information from the well. Like we have this A21 fracking results. So they were drilling these pilot wells, and then they were fracking them, and I had to see, okay, like, is this a success or not? And how would that update our beliefs? Then we built those inference diagrams here. So this is kind of for this extended reach well case. So you get this pilot well production, which will then inform your decision about the development. That will then inform your production for your B1. Like that's the first well you drill then, or the next well you drill. And that will give you more information again to decide if you want to drill a second well or not. And then you get some cash flows as well. And you convert that into decision trees. So this is kind of like a compact version of it. And then you get the solution, right? So these decision trees in the real example were like 1.2 million branches. So you basically can't show them anymore. So then you reduce the tree to kind of like a solution tree. So these are all the solutions given the uncertainties. And then you're looking for special cases. So this is just like zoomed in, where you see that in the, unfortunately, it's not ordered in the, so you have this production from the B1 well. If that is low, so like kind of a P90 and medium, like a P50 value, then your next decision will be to stop the production. You're not going to invest in a second well. But if you actually like get the high production, then it will tell you that you should drill the second well. And that we have done before we actually like drilled B1, before we actually drilled the other well as well. So we propagate all the uncertainties through, and it will give us already now a guidance on if we should drill the second well or not. And that is kind of like this proactive way of working in this setting. And then we can do some more analysis on what is the impact of the probabilities we choose. Like we ask, like, okay, what is the fracturing? What is the probability of success of the fracturing? So they were concerned that, okay, we could fracture, but we actually don't produce big enough fractures to produce. And then you will ask your engineers, okay, what is it? And they'll say, I don't know, 50%. And if you fall into the 50% range, you would go for this alternative 2, I've called it here. But then you can do some sensitivity analysis on that probabilities to see like how they impact your decision making. So then you have another choice here and you have another choice over there. And you start creating those cumulative probability plots where you see, okay, this black curve is like, there's no loss, but there's also not much gain in this case. So it's always dominated, except like in this case. And then you have those other lines which are fairly similar, but they help you a little bit to understand the risk picture instead of just giving you one expected value number to make the decision. And I think actually in that case, the expected values were fairly similar, where you would say like, okay, the decision criteria is expected net present value, but if they're all like in like plus minus 5% range, then you don't really know what to recommend. I think I'm gonna stop here then.
Very good. Thank you very much. Very interesting presentation, both of you.